In this video, we're going to continue looking at oblique asymptotes, and we're going to work through this chunky exam problem. So if you're feeling confident, pause the video and try all of this for yourself. So the curve C has equation y equals 5x squared over 5x minus 2. So immediately I see a sort of top-heavy algebraic fraction with quadratic over linear. I know we're going to get an oblique asymptote. Find the equation of the asymptotes. Okay, so let's work through part A. Well, the easy one is the vertical asymptote, because that's when 5x minus 2 is 0. So that's going to happen when x equals 2 over 5. So there's my first vertical asymptote. Now, for the oblique asymptote, I've got to do some division. So I'm going to say that 5x squared over 5x minus 2 must be equal to some amount of x plus some constant plus some remainder over 5x minus 2. Now let's put these together into a common denominator form, and I'll only focus here on the numerator. So the numerator would be ax plus b times 5x minus 2 plus c. There's the denominator, the numerator of the right. The numerator of the left is 5x squared. Expanding that right-hand side, I get 5ax squared plus 5bx minus 2ax minus 2b plus c. And that's got to be not only equal to but identical with 5x squared. Comparing coefficients. The coefficient of x squared is 5, so 5 equals 5a, and a is 1. Coefficient of x on the left is 0. And on the right, it's 5b minus 2a, so that's just minus 2. And I'm going to get that b here is 2/5. Finally, the coefficient of the constant on the left is 0, and on the right, it's minus 2b, so that's minus 4/5 plus c. And so c is 4/5. So this tells me that my equation can be written as 1x plus 2/5 plus 4/5 over 5x minus 2. And therefore, the oblique asymptote is y equals x plus 2/5. That is what our equation is approaching as x tends towards infinity in the positive or the negative direction. Okay, next, let's find the coordinates of the stationary points. This is going to have to be quotient rule here. So, dy by dx is vu dash. So v and u dash is 10x minus u v dash, which is just 5, all over v squared. So there's our derivative, and we need that to be equal to 0, which means that numerator is 0. Looking at this, this is just going to be a quadratic. So let's just expand that numerator. 5x times 10x is 50x squared, minus 20x, and then minus, what is that, minus 25x squared. And all of that should be equal to 0. So we're getting 25x squared minus 20x equals 0, and then solving that we're getting x equals 0 and x equals 4/5. But we don't just want x values, we want the y values as well. So subbing in 0, I get 0, so one of the coordinates is just 0, 0, and then subbing in 4/5, I get 8/5. And so there are the coordinates of our stationary points. Okay, on with part C. Sketch it. Okay, well, we've already worked out that the vertical asymptote is x equals 2/5. So let's put that in, relatively small. And we also have the equation of our oblique asymptote. If I go back here, it's y equals x plus 2/5. So 2/5 we've already got. It's this distance, so it's going to be the same one here, and it's just x equals that, so a gradient of 1. So there's our oblique asymptote. We've also got stationary points, which is useful. So we know that the point 0, 0 is a stationary point. So I'll do a little thing with a flat line through, which you can't really see there. And the other one is the point 4/5, 8/5. So 4/5 is here, and then 8/5 is going to be, well, I guess about here. I put a little line in like that. Anything else we can get? Well, there's the y-intercept and the x-intercept are both just the origin, so that's kind of it. So what do we want? Well, we know that as x tends to infinity, it's got to approach this line. So here it is approaching that line. Now we're going to reach our stationary point. Then obviously we're just going to have to go straight up to our asymptote there. And then here, well, as we go from x values that are above 2/5 to below 2/5, that denominator goes negative. So it's going to come back from here. It's going to reach our stationary point at the origin, bounce off, and head off to our asymptote like that. And there's a sketch. Now you notice that these sorts of functions very often have this sort of shape. The most common shape is kind of that and that, or it's mirror image. You can sometimes have that and that, or they sometimes have ones that look more like a sort of swoosh like that and a swoosh like that. So that's when they don't have stationary points. They kind of tend towards their oblique asymptotes in that way. So these are the kind of shapes that you kind of expect to see. Okay, part D is sketch the curve with equation mod of all of that and find an exact form set of values for which modulus that whole thing is less than 2. Well, sketching that modulus is easy because we've got our function. It's just the modulus of this. So that just involves leaving this bit alone and then just flipping the negative bit over and making it positive. So let's put in our asymptotes again. So we've got our vertical one there and our oblique one here. And this bit stayed exactly the same. So that bit that was there hit our stationary point and off to its oblique asymptote. Then we had, okay, we did have it going like this, but it all flips over, which means from the stationary point, which actually stays the same, it's going to go up to the vertical asymptote here. And now what's the line that it's approaching now? Well, it would have been this x plus 2/5. That gets flipped over as minus x minus 2/5. So you kind of got to imagine this flipping over like that. And it's now going to be approaching that asymptote this way. Okay. So there is our function. Now we need to know the exact set of values for which this graph is less than 2. Okay, well, there's quite a lot going on there because we worked out that this stationary point, if we go back a couple of pages, was 8/5, which is less than 2. So 2 is above that point. So what I like to do is kind of draw myself a line at the point where 2 is. And effectively need to be saying, I want all the bits that are less under that line. So it's going to be between here and here, and between here and here. So I just need to find those 4 points. So if I can find those 4 points, I'll be able to write down in a nice inequality when it's below the line. So let's start with this one, because this one I can simply solve by saying, when is the function less than 2? That's the function without the modulus sign. So that is, when is 5x squared over 5x minus 2, when is that less than 2? But I'm just going to say, when is it equal to 2 first, because I just care about these intersection points. And by the way, if we just go back to this graph, you'll see that this bit down here was never equal to 2, so that's just not going to be involved. That's useful. Okay, when is that equal to 2? That's quite easy to solve. 5x squared equals 10x minus 4, giving me 5x squared minus 10x plus 4 equals 0. And that gives me critical values of 1 plus or minus root 5 over 5. So this one here must be the 1 minus root 5 over 5, and this one must be 1 plus root 5 over 5. So between those two values, it is less than 2. So the first part of my answer is going to be x values between those two. So 1 minus root 5 over 5 is less than x is less than 1 plus root 5 over 5. So that's the first little region. The second region is the one over here, and that's when the sort of flipped bit of my function is less than 2. And I'm just going to find the points where it's equal to. Now, what is the flipped bit? The flipped bit is when this was multiplied by minus 1. So that is when minus 5x squared over 5x minus 2 is equal to 2. So we can just solve this now. Minus 5x squared equals 10x minus 4. And getting that all over to one side, we have 5x squared plus 10x minus 4 equals 0. And that gives me x equals minus 1 plus or minus 3 root 5 over 5. Once again, this is going to be the minus 1 minus 3 root 3 over 5 and the minus 1 plus 3 root 3 over 5, meaning the region we want is just between those. So the other part of my solution is minus 1 minus 3 root 5 over 5 is less than x is less than minus 1 plus 3 root 3 over 5. And these are the two regions that satisfy that. Okay, so that is our little look at oblique asymptotes, and I'll see you in the next video.